to mole ratio. So what the hell is a mole to mole ratio? Okay, all that is the units from our recipe where we can scale it up and scale it down, just like what we were doing in class last week. So if we need 2 cups of flour, 1 cup of sugar, half a stick of butter, we can scale that up. All right, well, I know that the flour and sugar are 2 to 1 ratio. That's what they're referring to here. Or I know that the flour and the butter is in a 2 to 1/2 ratio. Or we can say the flour is 2 to 12 cookies ratio. That whatever I put in on one side, I'm getting out on the other side. That's what the mole to mole ratio is. Now, why do we call it mole to mole ratio? Because when we have a balanced equation, our units is in moles. It could be in molecules or atoms, but that's too small for us to see. So we use moles when we have a balanced equation. That's our unit that goes along with it. So again, don't make this too crazy. Using our chemical recipe, we're predicting amount of products or amount of reactants. And that's kind of that last part that we get to. We can either figure out, well, how much flour do I need? Or how much butter do I need? Or we can figure out how many cookies can we make? That's it. That's all stoichiometry is. So again, it looks like chemistry. It's got math in it. But remember, it really is just using a recipe. It's just a recipe for chemicals instead. So we're going to do an example of this kind of together, and I'll kind of show you what it looks like. Vocab-wise, I'm going to mention this one because we are going to use this today. The vocab word that you need to get is this phrase called theoretical yield. So you should copy that down. The word is theoretical yield. That's a vocab word. Copy it down. Theoretical yield. So what does that mean? Based on my calculations, how much product can I make? Theoretical yield. Theoretically, based on my math, I should be able to get 12 cookies from this recipe. Y'all know that your actual number of cookies can vary, right? Because I don't know about you, but none of my cookie batter don't all make it in the oven. Theoretically, I can make 12. My actual yield may be like 4 by the time I'm done eating the cookie batter, but that's just me. Okay, so again, theoretical yield is based on the recipe itself, on paper, according to my calculations, how many cookies should I be able to make? What's my product that I can get out of this reaction? So theoretical yield refers to a product. Okay, theoretical yield, based on your calculations, that's what makes it theoretical. Yield means it's a product. How much stuff am I getting out? Again, different than my actual yield, because you may eat some of the cookie batter, you may burn some of the cookies, you may make them too big, too small. There's lots of things that affect your actual yield, but theoretically, you should be able to make a dozen. We good so far? Got the basic idea, I hope? Okay. All right, so what does this look like for us? Not that, not that. Come on, forward. No. Why is this being stubborn today? All right, so we're going to do this one as a first one. This is a relatively easy one to do. I need to get something going here lab-wise. So go ahead and copy that part down. Okay, I just turned on the gas, so under no circumstances should anybody be playing with the nozzles, the gas nozzles. Okay, so synthesis reaction. Synthesis reaction. We're going to do magnesium and oxygen gas. Go for it. Start writing your chemical equation. Magnesium reacts with oxygen gas. So see if you can write the reactants. What are the formulas for the reactants? Magnesium reacts with oxygen gas. You can do this. I just said write the formula for the reactants. Okay. Start, see if you can write your balanced equation. Yeah. There are two different reactants, so you need a plus in there. Come on. Yeah, what are your formulas for your two reactants? Why is this thing being such a pain? Okay. Now it's making noise. I'm trying to make the Bunsen burner go. What? What? Perfect. Perfect. Wouldn't surprise me. Come on. It's not that you're chill, it's just after a while you get used to doing stuff. Okay, why do you not want to let this? It's like a belt, which is the dumbest thing ever. I never found those to be the most useful objects in my world. There we go. All right, fire. Okay. All right, so in order to do any of these sorts of demos, I'm gonna get this stuff going, make that going. We'll take a look at it. So what's the formula for magnesium? Mg, right? It's just magnesium metal. That's all you got. So when we start off writing our chemical equations here, we got to start by writing our reactants. Mg. Oh, my board's way off. Hold on. I wonder it's not working right today. 2, 3, 4. There you go. Magnesium reacts with oxygen. Don't forget to put the plus in here. Magnesium is one reactant. Oxygen is the second reactant. So that we've got that. And it's a synthesis reaction. So a synthesis reaction means they're going to come together and form the compound from magnesium and oxygen. So what students forget to do at this point is they forget about balancing charges. When you're writing formulas, you got to check charges every time. So we got Mg, and then O are going to come together. What's the charge of magnesium? Look at your periodic table. Okay, look at the charge, right? This is a 2+. Charge of oxygen, it's a 2-, right? So this one is already balanced. It's just MgO. It's not MgO2. We don't just smush them together. So you got to think about what their charges are as ions. So it's kind of a separate step. All right, now, Okay, reactants, a single product, synthesis reaction. Got to balance it. You can use waffle if you want to. You can do this one by inspection. It's not a very big reaction. That's what the tic-tac-toe thing is for. There's no charges in this part of it. It's just the number. Yep. Remember, for this part, all you're trying to do is balance the number of atoms of things. I already have. Hey, guys, we got to make this a little bit on the quicker side. Otherwise, we're just never going to get to the lab part. So, balancing equations. How many magnesiums on the left? How many magnesiums on the right? How many on the left? 1. How many on the right? Okay. And again, this little tic-tac-toe thing is just a way to keep track of. That's all it is. How many oxygens on the left? Okay. Oxygens on the right? 1. Is it balanced? No, because the numbers don't match. So we need some more oxygens on the right. No, you're not allowed to do this. Remember, when we're balancing equations, the only thing you can do is put coefficients in front. It means if I've got 2 atoms of oxygen coming in, that means I'm making 2 of these. So we do coefficients out in front like that. It's been a little while. Now check your math. How many do we have? Now I've got 2 magnesiums, 2 oxygens. So I made the oxygens better, but now the magnesiums aren't balanced. That's normal. So how do we balance the magnesium? They put a 2 over here, like that, right? So there is our recipe. If we want to make our product magnesium oxide, this is now our recipe. This is what we're going to use. 2 magnesium atoms will combine with 1 molecule of oxygen gas, and I'll end up making 2 molecules of magnesium oxide. It's a 2 to 1 to 2 ratio. So we're saying, what's our mole to mole ratio? 2 moles of this would combine with 1 mole of that and produce 2 moles of that. That's our recipe. So when we're talking about a mole to mole ratio, that's all we're referring to is what are those coefficients. And our unit, when we're talking about those coefficients, is going to be in moles. It could be in single molecules, yes, but that's too small for us to see. It's atom reactions. So we always do it with moles. 2 moles of that, 1 mole of that makes 2 moles of that. So far, so good? So how much magnesium oxide can I make? If I want to know the amount of this that I can make, great. I can just do 5 moles of something, 5 moles of oxygen. I can make double that, 10 moles of that stuff. But what if we're doing it with mass? And this is the thing that makes it stoichiometry, because we're typically doing this with mass. So we're going to take a look at how much of something can we deal with. Now, it's really hard to measure the mass of oxygen. I can really easily measure the mass of magnesium. So let's find out how much this is. Now, when we're doing this, when I do this as a demo, our quantities are very approximate. So we're just going to calculate it and kind of figure out what this ends up being. But this is kind of what you guys are going to do. So here's my magnesium. There it is. This is 0.13 grams of magnesium. That's how much I got. I've got 0.13 grams of magnesium. Now, I know when I actually go do this reaction, I will never get the amount of product that I thought. But let's calculate the theoretical yield of magnesium oxide. So we're going to try to figure out theoretical yield is the mass of the product. So we're going to practice doing this. You ready? Okay, so we're starting with 0.013 grams of magnesium, and I want to know how much of that we've got. So here's how it goes. We need to use a mole to mole ratio. Are we in moles? Can we get to moles? Yeah. 0.13 grams of magnesium. Now, how do I convert this to moles? Sekunde fractions, yeah. Yeah. And we use the molar mass from the periodic table, yeah. It's very good. So go find the magnesiums at number 12. 24.3? Yeah. Okay, so again, follow the units. Grams has to be down here. Notice how I'm putting units and labels on there. I'm not just saying grams. And then now that we're starting to do chemical reactions things with before and after, it's more important to do that. You have a periodic table in your hand. So it's really important to not just say grams, but to say the grams of what, because we're going to switch from a chemical to a different chemical here in a little bit. So grams of magnesium, 2 moles of magnesium. Our first step in stoichiometry, write this on the side sometimes. Our first step in stoichiometry is to convert 2 moles. Now, if you're given moles, then that step's taken care of for you. But your first step is always convert 2 moles using molar mass. That's always our first step. Again, if I give you moles, great. You don't have to do that step. It was taken care of. But if you're not in moles, you got to get 2 moles. That's always step number 1. 24.305? Okay, well, 305, 30, whatever, fine. That's equals to 1 mole. Remember that number from the periodic table always goes with grams. And we can figure out what this is. So this is that calculator part. How many moles of magnesium do we have? Not very many. 0.305. 0.5. We do got to kind of check sig figs. Sig figs. We're doing 2 sig figs in this problem because that's what I'm given. So it's going to be 2 sig figs that we're going to work with kind of all the way throughout. So that means our answer here, as I have on my calculator, 0.056399 and more, right? 0.13 divided. What? Something is not working correctly on my calculator. 24.305. This calculator's got sticky buttons. Okay, hold on. 0.0053486. Yeah? That's more what we're looking for. Thank you. 2 sig figs. No. You can only have, you have to round it to 2 sig figs. We've only got 2 digits, so our number here is going to be 0.005. And then we got to look at our next digit. Here's our 2 sig figs right here. Zeros don't count, liters don't count. So is it 5.3 or is it 5.4? What do we do? Round up or leave it the same? Leave it the same, right? Because it's 5.3 moles. Okay, liter zeros are just placeholders. Because if I write this in scientific notation, it's 5.3 times 10 to the negative 2. Those are just placeholder zeros, so they don't count. Zeros at the beginning of a number never count. It's been a while since we've done that, a long time ago. That's why we're reviewing. This is a good thing to do. Okay, so now we've got our moles of magnesium. This is now step number 2. Step number 2 is to use our recipe, mole to mole ratio. Step number 2 is to use our recipe as a mole to mole ratio. Because I've got 0.0053 moles of this. How many moles of that can I make? This is the mole to mole ratio step. You should write that down. Step number 2 is to use your mole to mole ratio from chemical A to chemical B. So here's what this looks like. Well, if I had 2 moles of magnesium, how many moles of magnesium oxide could I make? 2, right? If I have 1 mole of magnesium, how many moles of magnesium oxide can I make? 1. If I have a half a mole of magnesium, how many moles of magnesium oxide can I make? A half, right? So again, it's in this case, they're equal numbers because it's a 2 in and a 2 out. So that makes it nice. Here's how we do it in dimensional analysis for when the numbers are not nice. Okay, so here's one to fraction number 2. 0.0053 moles of magnesium. So again, this is step number 1. This is step number 2. This is our, this is our mole to mole ratio step. So we've got moles of magnesium here. That's what needs to be on the bottom here. MOL of Mg. This is our original material. What are we trying to convert to? Magnesium oxide, right? That was the product that I asked you about. So the bottom is the old unit. The top is going to be the new unit, which is moles of magnesium oxide, because that's what we're looking for in this question. What is our mole to mole ratio here? This is from the recipe. What's our mole to mole ratio? 2 to 2. And we're not talking about oxygen in this case, so we don't need to put that 1 in here. We're just talking about those 2 chemicals. 2 moles of magnesium, 2 moles of magnesium oxide. So that's where this is going. 2 moles of magnesium, 2 moles of magnesium oxide. This is the mole to mole ratio from the balanced equation. That's what this step is. This is from the equation. Again, you guys should write that down because you're not going to remember this later. Where'd the 2's come from? Why'd she put the 2's in there? Now, I do ask me this all the time. Well, if it's multiplied by 2 and divided by 2, can I just write it as just a 1? You can, don't. Most of the time, it's not the same. So don't get in the habit of just writing the wrong numbers there. Put the actual numbers from the chemical equation in there. Wait, what? Sorry, what is the M2M? Mole to mole from equation. Mole to mole ratio. From the balanced equation. 2 moles of magnesium, 2 moles of oxygen gas. So make yourself... Why are they the same number? Great question. Because in our particular recipe, 2 of these makes 2 of these because the recipe has the same number. In this case, they're the same. No, that's great. So math-wise, well, 0.0053 times 2 divided by 2. Yeah, it's 0.0053 moles of magnesium oxide is how much we should be able to make. Which one?
You got 5.3 times.
Same answer, same number. Yeah, no, that's this in scientific notation. That's all it is. All right, so we're close. My question was asking me for how many grams of this I want. We have moles. Can we convert back to grams? Yeah, that's it. So we're going to do 0.0053 moles of MgO. This again, step number 3. Theoretical yield is in grams. So I just want to know how much this weighs. So again, cross down, convert up. Moles of MgO on the bottom. Crossing the units down. Can I convert up to grams of MgO? Yep, MgO. This is a molar mass step. Can I convert from moles to grams? Yeah, molar mass. Where do we get the molar mass of magnesium oxide? On the periodic table, right? How much does magnesium weigh? How much does oxygen weigh? Just add them up. 40.31 I'm hearing? That's someone has suggested 40.31. I haven't done it. Anyone? Confirmation?
Yeah. Well, I got 40.3.
Oh, 40.305 basically, isn't it? Yeah, but it's not 15.99. Remember, we're using 2 sig figs. It's either 15.999 or it's 16.0. So we do 2 decimal places on molar mass. So yeah, it's 16.0 when we do oxygen. 16.00 actually. So whatever, just leave it like that. It's fine. It'll work itself out with sig figs anyway. So find out what's your answer. How many grams of magnesium oxide can we make? That times that divided by that. We're just doing a molar mass conversion. So we had moles. What was that? 2.14? Confirmation?
Yeah, 0.2136. So yeah, 2.14.
And the -1? I think 2 grams is too much.
Yeah, 0.214.
0.214 would make more sense. 214. 2 sig figs would be 0.21 grams of MgO. So our theoretical yield, yeah, it's okay. Theoretically, when I burn this piece of magnesium, I should be able to get up to 0.21 grams of magnesium oxide. I never will, because you'll see why as soon as I do it. Yeah.
Okay, I'm gonna look right at it.
Okay, question? Yeah. So the question she just asked was, do we go to the hundredths because of the masses, or why are we rounding it to 0.21? Okay, our original mass that we're dealing with has 2 sig figs to it. So that means when we're done, our answer only gets 2 sig figs. Yep, great question. Okay, so here's what this looks like so you can see it. So we can actually see what the magnesium oxide looks like. I'm just doing this because goggles and glasses are not friends. So let's figure it out. Again, I know I'm not going to make all of this. Now my voice starts sounding really weird after a bit. Let me fix this here. Come on. I know, right? Okay, so I'll tell you right now. There we go, get that adjusted. Don't look directly at it, or it'll be the last thing you see for a little bit. Don't look directly at it. No, I won't. Now you really want to look at it. Give it a sec. There we go. There you go. Ah. But don't look directly at it. Ah. Yeah, now it's like the last thing that you see, right? Fireworks. You guys have seen fireworks, right? Yeah, but they use this stuff all the time. So this is a really common material that they use in fireworks. Yeah, no, I told you not to look at it.
I did it anyway.
I know, right? So,
Well, you can tell me to do a lot of things.
I know. So, yeah, super white sparklers, by the way. You get the little tiny sparklers. It's little tiny granules of magnesium. That's what's producing that bright, hot white light that you get to see. When you see fireworks that are bright white, or like the big flashbang ones, it's magnesium or magnesium that's in there. It's making that super, literally just metallic magnesium. And what is that? This is the magnesium oxide. That's what this is right here. Magnesium oxide. That's what we just produced. So, judgmental. Wow. This stuff? No, you cannot relight because it's already been reacted with oxygen. So it's not going to want to react with oxygen again, right? So it's reacting with oxygen in the air. Yeah, I have to give it a lot of heat to get it started, but it's just reacting with oxygen. So this is what magnesium oxide looks like. There's still a little bit of unreacted magnesium on here. It never burns all the way. So that's why if I weigh it right now, I'm definitely not going to get that value. Plus, you saw a lot of the smoke go up, right? And that smoke is powdered magnesium oxide that's going up in the air as well. So we're not really collecting all of it. That's why it's called yield is going to be quite a bit less than that when I weigh it. Does that make sense? But this stuff is definitely different material. It's cooled down enough now. It's powder. So it's not metal anymore. It's a real different material in terms of what it looks like. So again, just sort of a white powder, like almost like an ash, but that piece is, will that go? What was that? Why would you do that?
Why wouldn't you do that?
You guys are crazy. I don't know if that last piece will get or not. We'll go. Yeah, there it goes. Yay. You do kind of have a point there, actually. So there you go. All right. So yeah. Yeah, exactly. You guys are kind of nuts. All right. No.
What about legal fireworks?
No.
Why not?
No.
Sell them for profit.
Okay. So, all right. I'm gonna turn this down. I do turn this guy down. All right. So, again, if I go and weigh that white powder, is it going to actually weigh the whatever we decided was what is it, 0.21? Our theoretical yield here would be 0.21. Are we actually going to get 0.21? In the real world, no. In a perfect world, if I did this in a closed container, captured all the smoke, had all that stuff sealed up, then yeah, we could probably get most of it. But that was definitely not 0.21 grams. Again, a lot of it goes up in smoke and is just in dust particles, which you can't really collect. Some of it's unburned magnesium, etc. But again, that's that theoretical yield. It's that mass of magnesium oxide that we could do. How are we doing so far? Are we all right? Okay, so we're going to do one more with some magnesium and some fire. I'm not going to do another. I'm not going to burn it this time. But we're going to do a second reaction. We're going to practice this. And I'll show you how to do this in one wonder fraction as opposed to 3. You can do this in one single long wonder fraction with 3 steps as opposed to 3 smaller ones. You can totally choose which approach you want to do. If you'd rather just do the 3 small ones and get 3 answers, great. If you want to do it in one long one, also great. It works the same either way. Okay, all right? So here's reaction number 2. Forte, let me see if I can find it. Where is it? There we go. All right. All right, here we go. Reaction number 2. So we're going to take a different piece of magnesium now, and we're going to react it with aqueous hydrogen chloride, also known as hydrochloric acid. So hydrogen chloride is one name for it. Hydrochloric acid is a different way to name the same thing. It still works. So let's start by writing our equation. We got to get our recipe for this to be able to predict what our products are. And figure it out. So magnesium again. So write your formula for that. That's an easy one. This is atomic magnesium, doesn't have a charge. And then hydrogen chloride is the compound that you were trying to write the formula for. So find your charges. I'll tell you what that means in a sec. No, it's just hydrogen chloride. We'll talk about what aqueous means in a second. I'll talk about aqueous in a sec. Hydrogen chloride. Okay, what's the formula for hydrogen ions?
CO2.
Chloride. Okay, that's chloride. Chloride, hydrogen, Chloride, IDE, tells you it's just chlorine by itself. It's not a polyatomic. So there's Cl. What's the charge of hydrogen ions? What's the charge of chloride ions? Minus. So these are already balanced, so we're set. Okay, so let's predict our products. This is now a single displacement reaction where like kicks out like. Like displaces like. So hydrogen for this is considered to be a metal, even though you're more used to it as a gas. So like kicks out like. So what are our two products going to be? Yeah. Magnesium and chlorine is going to be the new partners, and then hydrogen is going to be other one. We got to finish our formulas. We're going to have magnesium and chlorine are going to end up being together. Magnesium is going to kick out the hydrogen, and then hydrogen is going to be kind of by itself. These are not done yet. We're starting to predict our products. Again, this is single displacement. Like kicks out like. Magnesium kicks out hydrogen, steals its girl. Hydrogen's lonely. So we have to finish writing our formulas. Charge of magnesium as an ion now. What's the charge of magnesium? 2. Charge of chlorine as an ion? 1 minus. So fix it. It's not done yet. Okay, symbol charge, cross them down to get the final formula for it. So it's MgCl2. We need 2 chlorine to neutralize that magnesium. Hydrogen's a gas. So what do we know about the formulas of our gases? Like oxygen gas. What do we know about our gases? What are their formulas like? They always have that little 2 down there. They're diatomic. So hydrogen gas is like that as well. Okay. Hydrogen is an elemental gas. I'm telling you that so that you know it. I don't expect you to memorize that. Yeah.
So is that done just to help balance it out? Because
No.
having a 2 plus, now chlorine has a 2 minus, now hydrogen has a 2.
Hydrogen does not have a charge to this. This is just its elemental form. All right, balance your equation. So the next step is balance your equation. Get the whole equation balanced. Left side, right side, balance your reactants and products. We now have our basic recipe, but we need to get our ratios for it. So balance your equation. Let's see. Balance your equation. Balance your equation. Let's see. I need that. And then, where's my others? Good. Give me 1 second. Give everyone a chance to. All right. Okay. Annalyle thinks she's got it. What do you think it is? So, by the way, if you're not sure, M, G, H, and Cl. There's 1, 1, and 1, and then there's 1, 2, and 2. So what do we got to do to balance this thing out? Anna, you said it. What was it? A 2 here? Yeah, there you go. That's it. All right, so that equation is now balanced. So now we know what our mole to mole ratio is. 1 to 2 to 1 to 1. 1 to 2 to 1 to 1. 1 and a 1. What was that? 2 is just on the left side. Okay. Okay, so how do we read this? Yeah, 1 mole of magnesium will react with 2 moles of hydrogen chloride and can produce 1 mole of magnesium chloride and 1 mole of hydrogen gas. So it's a 1 to 2 to 1 to 1. That's our mole to mole ratio. What was that? Uh-huh. Yep.
I got most of them right, but I had to do it.
That's kind of true now, isn't it? All right, so in this particular case, our magnesium weighs, how did I get two identical sized pieces? 0.13 grams. So 0.13 grams. I just happened to get the exact same size. I was not trying all that hard. All right, so when I put these two things together, and I'm going to do it here in just a second for you. That's our piece of magnesium, 0.013 grams. We got that. By the way, what does this word mean? Oh, let me mention that really quick. Aqueous. What does that mean? We would abbreviate it like this, AQ, like that. All that means, that term aqueous, that means it's a solution. It's dissolved in water. That's what that means, aqueous, okay? So like you have like salt and you're making pasta with it, you're making NaCl that's aqueous, salt water. The water is not a reactant. It's just the pool that everyone else is swimming in, okay? It's a pool party, right? But again, the water is not a reactant. We don't write water in the equation, but it's occurring in solution is all that means. Those ions are there for those little things to, the water molecules are there for stuff to swim around in. So what should we make? What do you think this is going to look like? No, we're in school. What do you think this is going to look like? I'm going to take a piece of metal and I'm going to stick it into a clear liquid. Take a look at these.
I think it's going to become it's going to become an upgrade.
Okay.
It's
So
going to be a gas.
that's a gas. So what is that going to look like? Bubbles, right? And this magnesium chloride, you guys know what magnesium chloride looks like because you've actually seen something similar to it. Looks a lot like sodium chloride in water. But mag chloride is the stuff that they put on the roads. Mag chloride, that's what it is. Yeah, this is road salt, liquid road salt. It's just a solution is all it is. So this is going to be a clear liquid. All right, so let's take a look at it. Here it is. This doesn't look all that exciting, but I'm going to try to verify kind of what this thing is. I want these guys to be out of here. I'm going to move these over to your table. Actually, I'm going to move these up to my table. I don't need that there. So I'm going to take some hydrochloric acid. Hooray. So I like the smaller flame of the candle. Just that's all. I can use the big one. It's mood lighting. All right, so this is hydrochloric acid. That's what that stuff is. This is strong enough to make this happen kind of fast, but not super strong that like we have to evacuate the room. It's not that kind of strong. But that 1.0 M that's at the top, that just tells me kind of what the concentration is. That just tells me that I don't want to get this on my face or in my eyes. I don't really, it's not going to burn my hands too much, but don't want it in my eyes. So there we go. Nothing exciting yet. Ooh. Wow. Ooh. Yes, all I did was pour it into a beaker. Very exciting. Okay. All right, so I'm going to drop this little guy in here, and you'll see what it happens, what it does. So remember a long time ago, we talked about the the signs of a chemical reaction: change in color, change in temperature, formation of a gas, or formation of a solid. Those are the four things. Formation of gas is bubbling. Formation of the solid is called a precipitate. It's where it turns color and gets kind of cloudy, right? So here it's. Can you see the bubbles? You can see them. There is bubbles. It's not super exciting. Like, whoa, look at it go. Well, so now I want to catch the gas that's on here. Okay, that's going to be the more fun part. So I'm going to actually catch the gas. Not super high tech, but that's why I'm putting this over the top so I can capture that gas that's coming off, because it's gonna just sit there and kind of react for a little bit. So we're gonna give this a few minutes. It is getting kind of warm. We'll let it sit there and kind of keep going for a little bit, but we'll let it go. Oh, where'd it go? Hold on, come here. Yep, there we go. I'm just gonna let that kind of sit there and do its thing. So we're gonna try to figure out how much of the hydrogen we're making. That's what we're gonna start doing. So while this is reacting, I'm going to have you guys start to do the stoichiometry. I want to know how much hydrogen I can make. Hydrogen is what we're trying to find. So we're trying to go to hydrogen. So that's what we're trying to find. We know how much magnesium we started with. I want to know how much hydrogen I can end up with. It's very similar steps. You can see it. There it goes. Bubble, bubble. You guys can see it? Bubble, bubble.
Yeah.
There we go. You guys go so you can see it. Okay. So there you can see it. Okay. All right. So just so you guys can see it. Bubble, bubble. Doing its thing. There you go. You can see it. The acid's literally eating the metal. There you go.
Wow.
It's warm. You can touch it. Touch that. Definitely getting warmer, right? I'm just collecting the gas on the top. There you go. So, yeah. You don't. Anytime you're not inhaling oxygen, that's bad for you. Just like helium, if you inhale too much of it, you're depriving your brain of oxygen. So, it's not going to kill you for a short amount of time, but for a long period of time, definitely not good. Okay. There you go. You can see kind of what it looks like. And it's doing its thing. You can feel it. It's warm. It's not hot, but it's warm. Yeah, so you can it's definitely kind of changed the temperature. There you go. Yeah, it's warmed up. It's just room temperature stuff. Yeah, it kind of looks like it, right? So here you can kind of see what it's doing there. It's doing its little bubbly thing. And it is warm if you want to touch it. You're welcome to. You can just see. It's not hot, but it's warmed up because it was just regular room temperature.
These ones? Because we need to change it to this to get the H.
No, you can just go right to here. You're going to this product, just to H2. You don't need to go through every other reactant. I just want to know how much, if I start with that and use up all of it, how much of this can I make?
So I did that the first step.
That's correct.
And then I only do this step, but with this ratio.
To the hydrogen. What was that? Yes. I just can't write you a pass because my hands are full. Okay, so you want to see it? You guys get a chance to see it? Uh-oh. It's gone. Touch it. Yeah, it's warm. Yep. And it literally ate the entire piece of metal. It's gone. So at this point, it ate all the metal. It's gone. Yeah, you can touch it. It's warm. Okay. All right. Yep. Ate the whole metal. All right. Here you go. Ate the whole metal. Here you go. You can touch it. So it's warm. Okay. All right. So, ladies and gentlemen, I'm gonna finish this demo here really quick, even though you're not done with your math yet, since I'm not carrying around a vial of acid, whatever. The metal is now gone. It's no longer in there. So you can see it's just disappeared. It has completely dissolved the metal. So now that magnesium is now in the dissolved format. It's in the salt. So it's in the MgCl2 form. We don't have any of the Mg left over. We've used it all up. So what we're going to do is we're going to test for this gas to see if it's actually hydrogen or not. So I'll show you what the hydrogen test looks like. So there's some things you may know about gases. Oxygen. Fire, right? It just burns, though. I mean, you need to have oxygen for any sort of combustion. How about CO2? It actually puts it out. Most fire extinguishers that we have, a lot of times, are CO2 extinguishers. They'll deprive the fire of oxygen and literally starve it. Neither of those. This is hydrogen. What? Yes, dry ice is solid carbon dioxide. Yep. Yep. Absolutely. Same stuff. Yep. Same stuff. Buying dry ice. Fire extinguishers are expensive. Yeah. This is neither of those. This is hydrogen. So hydrogen gas, very flammable, as in Hindenburg. Yeah, the Hindenburg was a lovely thing. Now, one of the things that's nice about hydrogen is it's lighter than air. So it used to be, I just wish I was alive at this time. It used to be that when we gave little kids balloons, they had hydrogen in them. Because hydrogen floats, which is why I'm holding it this way, upside down, right? Because hydrogen floats. But hydrogen's really flammable. Helium is not. Helium is that far right. It's a noble inert gas, right? So it doesn't do anything. But you don't want to give somebody a balloon for hydrogen. So let's see if this works. Yeah. All right, so. All right, so ladies and gentlemen, put your pencils down. Listen over here for a second because this is going to happen only once. All right, this is only going to happen once because I'm not going to make more. No. So when you burn hydrogen, I don't need this one. When you burn hydrogen, it burns super fast. And so what this is going to do, if it's working correctly, if I did it right, And if it didn't, I'll try it again. But if I did, this should be full of hydrogen, right? It's going to burn so fast that the fire is going to go up inside really quick. You won't be able to see it. It'll happen like super quick. And in the process of doing that, it's going to actually like, how do I say this? It's going to suck, literally. It's going to use up the hydrogen so fast that it's going to try to slurp in oxygen from the outside. And it's going to make a sound that might sound like this. Whoop! I'm not making it up. You'll see. I'm actually doing a pretty good impersonation of that. So let's see if it works. We'll see if it did or not. So I'm going to this is just a test to see if it's hydrogen or not. So we'll see if it goes or not. Are we ready? Hopefully. Come on, my friend. Come on, you can do this. Oh. Let me try it again. I get you all built up and then it doesn't even work. Okay, let me try one more time. I missed my hydrogen. Hold on. What was that? Because, good question. Because you don't want something that's, why? You don't want something that's potentially flammable over something I have less control over. Does that make sense? If I drop this or do something weird, now I've got flaming things and gas and other stuff at the same time. Let me get another piece of magnesium. I'll try one more time. I just lost my mojo. Yeah, because it'll escape the way it's set up. It'll just escape out of there. All right, so let's do this. You can get in there. All right, let's do one more time. What was that? Molar mass. Let's see. Grams. So we got moles to moles. Is it 1 to 1? 1 to 1. Yep. And then it's that to grams. Yeah, you're almost there. All right, let's try one more time here. See if I have enough. Let's see if we got enough. Hold on. All right, I'll try one more time here. Let's see if we got enough in here. All right, hold on. You can see the smoke coming out of this. Okay, let's see. I told you I did a good impression of it, didn't I? All right, I'll try one more time. I told you it's like a chihuahua, right? It's actually a barking dog reaction. Is really common to call it that because it literally sounds like yeah. It's not nice. Don't do that for real. All right, so I'll try one more time. See if there's enough still in here to do it. I might be able to get a little bit more in here. All right, hold on. Okay, all right, one more time. Oh, there it goes. All right, so anyway, there you go. So that is what the hydrogen sounds like when you burn it up. So all right. So I'll blow this guy. Blow it out with my mask on. There we go. What was that? Hold on. Can you what? It can be, yeah. It's not all of your notes, but that's part of it, for sure. All right. Well, I think that was more like the screaming that was happening in there. All right. So let's finish this up. How much hydrogen did I just make in that first piece? Well, I didn't catch a lot of it. So here's how to do this in a single problem. A lot of you guys are doing it in 3. Perfect. It's totally fine. You can always do this in 3 steps. Step number 1, convert to moles, grams to moles. Step number 2, convert moles to moles, get the other chemical. Step number 3 is moles to grams, get it back to grams. So everyone's going to say this with me. Hold on, give me a second. You're going to say grams to moles, moles to moles, moles to grams. That's what we're all going to say. It's the chemistry song. Ready? Grams to moles, moles to moles, moles to grams. Okay, one more time with feeling. Grams to moles, moles to moles, moles to grams. That's what we do every time we do these problems. If you can kind of remember that in your head, it'll help. So step number 1, grams to moles, 0.13 grams of magnesium. So we're starting with what we're given. We need to do grams to moles. Grams on the bottom, moles on the top. Grams of Mg to moles of Mg. This is molar mass. Grams to moles. So what is our molar mass of magnesium? 24.305, right? Because that's from the periodic table. Okay, regardless of what we start with, the number in our conversions here is always 1 mole. So grams to moles, what's our next step? Moles to moles. So we don't have to hit equals here. We can keep going. It's dimensional analysis. So if this is moles of magnesium, this is going to be moles of magnesium. This is our moles to moles, bottom to top. Moles of magnesium. And what are we trying to find? Moles of H2, right? Hydrogen gas, because that's what I asked for in this one. I could have asked for this one, but I asked for the other one. So grams to moles, Moles to moles. What is our mole to mole ratio here? One of these to one of those. So it's just 1 to 1 in this case. That's easy. Sometimes it is, sometimes it's not. And then our last step, grams to moles, moles to moles. Moles to grams is the last one. So again, moles of H2 to grams of H2. 1 mole of H2. Close. It's 202 because it's hydrogen H2. So again, you have to kind of take that formula into account. Hydrogen gas has a molar mass of 2.02 because there's 2 hydrogens in it. It's 1.01, but there's another one. So it's 2.02. Again, that's the molar mass of hydrogen gas. So now this is one step. Now you can just do the math all at once. You don't have to do the math 3 different times. You can just do the math once. Multiply across the top, divide by the bottom, and you can figure out what your final answer is, how much hydrogen that was. And then we're going to get started on our chemical that we're going to do. 0.13 times 1 times 1 times 2.02 divided by 24.3305. Yeah, I got a small number, right? 0.10880431, something like that. Okay, so 2 sig figs is what we started with. 2 sig figs for our answer. 0.011 grams of H2 is our final perfect answer. So that's how much we actually just burned there. Okay, what did you get?
I got 0.0108.
Yeah, and then you're rounding up. You did get it. Yep, nope, you got it. Yeah, no, it's hard to see from that corner. Okay, so your job, I'm going to get you guys set up to do your lab. If we have some time when we're done, we'll come back and do a couple other little demos here. But you're working and setting up the lab that you guys are doing. So here's the lab that you guys are doing. Hold on. I'm going to go back here. You guys are going to be making silver. You're literally going to be creating silver for this lab. So truly silver. So it is a single displacement reaction. You'll be given some copper and some silver nitrate. So with your partner, this is only 2 people at a time, and I'll come around with this in a second. I want you to start writing the balanced chemical equation. It's a single displacement reaction. You've got your periodic table, so look at the charges of stuff and figure out what you're going to make.
So I'm guessing we're treating silver as a gas.
No, it's a solid.
Oh, so that means we are doing it silver 1 plus.
Okay. Figure it out. Copper is reacting with silver nitrate solution. Okay. Start writing your formulas. We'll try to predict our products here. I can take this off for now. Hair's stuck in it. Yeah. What? Silver nitrate, yeah, I know. But whatever, it's fine. Figure it out. Okay, we don't have a ton of time on this, so let's get going relatively quickly. Don't have a ton of time. S is solid. Okay, I'm going to put this here. Okay, this is for your guys' tables. Watch out. Yeah, there you go. All right. This is for your guys' table. Yeah. Figure it out. Ag plus NO3, or AgNO3 plus Cu. Okay. This is your table. This is for your table.
Wait, how do we? Oh.
It's copper 2 is going to be your product, or one is the ion form on the other side. All right. Yeah. Yeah, go for it. Use it. Go for it. I'm going to do this. Hold on. I'm going to put that there. What? Okay. Okay, like displaces like. Copper 2 is formed, by the way. The ion form of copper is copper 2. The ion form in the products for copper is copper 2.
So would that be the answer?
Still has to be nitrate. Just remember, nitrate's still always NO3. That's always nitrate. That's not going to change.
It's always.
Uh-huh.
But that's a negative.
But it's got a -1 charge, and the copper has a 2+ charge. So
It's just the
balance your charges. Copper's a 2+, nitrate's a 1-. Parentheses. I'll say a second. Okay. Predicting our products for this. These two guys are going to switch spots. Displaced like. So silver's going to come out. That's actually we're going to try to catch because that's kind of cool. And then our other product has got to be the copper and the nitrate go together, right? These guys are going to be together. Copper is a 2+ in this product. I'm telling you that. So it is copper 2 in our product. Finish writing your formula. This is close, but that's not quite it. That's close, but not quite. Again, I'm telling you it's copper 2. I'm telling you it's copper 2+. I know. So you got to fix that. 2+, 1-. When you've got polyatomics, hello.
I need carry in from my team.
Gotcha. Front table right there.
Where?
Yeah, right here. Hello. Carrie.
Hi.
This is Carrie.
Hi.
Carry in.
All righty. So, all right. So once we got this part taken care of, again, we figured out what our products was. Copper and iron or copper and silver switching places. Copper's a 2+ because I told you that. You don't know that from looking at the periodic table. Nitrate's always a 1-. So that's why we got to have parentheses around the nitrate. CuNO3 2. And does that make sense? Yeah.
This would now be 3 and this would be
Yes. So now balance your equation. Yeah, absolutely. Balance your equation. You got to have the whole thing. Now we got our general recipe. Now we got to get it balanced. We need our multimole ratio. Yeah, but not yet. We have to balance first. The equation is not balanced. Oh, you did?
In chemistry, there's no measurements to send it.
1, 1, 1, 3. 1, 1, 2, 6. Remember when you're counting. So we need to have more nitrogens and oxygens on the left side. Two, 2, 6. And that means we need a 2 there. All right. So here's what we are going to do at this point. So I need your attention for a couple more minutes. So here's what we are going to do at this point. So at this point, we're going to take a pause. We predicted what our products were. We finished our formulas of our products, figured that out, balanced the equation. So now we have our multimole ratio. So now what we need to do in order to be able to predict how much silver we've got, we need to have some starting information. So what your job is going to be to do right now is going to be to collect those initial masses, the mass of the silver nitrate and the mass of the copper. I'm going to come around with these in just a second. So I need your 100% attention because there's about 10 to 15 minutes left in class. And we have to get this done before we leave today. So is everybody ready to be listening to me? I should see everybody's eyeballs at this point. Okay. So I just gave every table a tub of material. That material is for the whole lab, and it's for second period and third period. So not everything in there is for use to use right now. So just keep that in mind. But there's enough for each pair of people to do this. Okay, so it's a partners, not a group of 4 kind of thing. So you've got a test tube rack, you've got some test tubes, you got some beakers, all this kind of stuff. You're not using all of this right now. So what you're going to need to do is get out, so please listen, you maybe write this down. What you're going to need to get out of that beaker, or of that tub, is going to be the small beaker, or one of the small beakers. You're going to need to use the stirring rod. You're going to need to use one of the test tubes, and the test tube rack. I think that's all we need. So I'm going to come around and give each group a sample of silver nitrate. So this is what silver nitrate looks like. It's this, or it's kind of white. So 100% of your attention, please. Silver nitrate is highly toxic. Very toxic. Okay, so be aware of that. You don't want to get this stuff on your skin. Definitely don't even joke about eating this. That's immediately you're out of my room. Okay, so like that's no. So again, highly toxic. This stuff is not nice. Silver is not so bad. Silver nitrate is incredibly poisonous, toxic, okay? Second thing that you need to know about this is that this stuff does cause chemical burn. Weird how they work. It's almost like, I can actually see some of it on me. It almost looks like you got little marker spots that's on you. So tiny exposures to it isn't a huge deal, but if you start, you actually touched chemical. Yeah, that's not good. So we want to be careful with this. It will stain your skin and it doesn't come off. So I don't want to say like henna because it's not safe like henna is, but kind of like that where literally kind of burn your skin and you'll have some funky colors going on in there. So you need to know what the mass of this is. And the way you're going to do that is with your small little beaker that you've got, you're going to eventually make a little solution of this. It's going to be silver nitrate solution. That's what it says up there, silver nitrate. Weigh your beaker, then put this into the beaker. Not with the test tube. Transfer this chemical into the beaker, and then you'll know what your mass of your silver nitrate is. Okay, makes sense? Then you're going to add water to this, about 40 to 50 milliliters of water. You've got the squeeze bottle of water that's in there, and dissolve it. Okay, so far so good? I need to know the mass of this, though, before you add water to it. The water's not a reactant. I don't want that mass. So I need to know this mass first. But again, you're going to put it in here, add about 40 or so, 50 milliliters of water to it. Stir it, glass stirring rod. Okay, that's what the glass stirring rod is for. Then, to do the reaction, we're going to do the reaction in a test tube. So I'm going to come around with a piece of wire for you as well. This is our copper reactant. So you need to know what that thing weighs. This is an easy one, right? Just stick on there, weigh it. And then you're going to do 2 things with this copper wire. Number 1, you are going to kind of polish it a little bit. There's some oxidation on the outside. Just take the steel wool and just rub it on there. Literally just kind of run your fingers over it and just go squeeze like that. It'll make it bright, shiny. So that's what that stuff is for. And then you're going to make this funky little coil, wrap it around the test tube or wrap it around a pencil, whatever, so that it just hangs inside of here like that. And then you're going to pour your solution in on top. So this is going to be dunked into the solution and it's going to react over the weekend. Does that kind of make sense? So again, you need to know this mass. You need to know your silver nitrate mass. You're going to make your silver nitrate into a solution, dissolve it. And then when you're ready, that solution into the test tube, put the test tube in the test tube rack. Okay, we good? Okay, all right, so start grabbing your materials. I'll come around with the other stuff that you need. Copper's in there for you. Copper's in there for you. There's one of those for you. One for you. One for you.
Thank you.
Yes. Here's one for you. There's one for you. There's one for you. Yes. It's 2 and 2. You're only working with a partner. One for you guys. And then there's one for you. You're going to do 2 groups, right? Or are you going to do 1 group? Just do 2. Do 2, whatever. It's fine. You got it. You want to just do 1? Yeah. Why am I giving this to you? That's a horrible, horrible idea. There you go. Okay. Okay. So this is 2. This is. Hold on. Okay. 1 second, 1 second, hold on. So here's number 2 for you guys. There's number 2, there you are. Okay. Okay. Okay, and there's, are you gonna do this as one group or 2? You're gonna do this as, okay, so we're gonna do this as 2 then. There you go. There you go, got it. Okay, there's one for you guys. Yes, indeed. Okay, I'm gonna turn this off. There's one for you, and remember there's fire behind you. I'm gonna turn that off in just a second. There's one for you guys. There you go. Not explosive, toxic. Okay.
So we do this, and then we see what's this, and then we put it in here so we can find the massive silver nitrate, and then we do the solution with that. But I don't know, do we do the solution with that? Or is
With,
it
yeah, water, this stuff.
how much did you say?
40 or so. Fill it up
We put it in
in the test tube.
and then we put it in the rack.
Mhm.
Oh yeah.
Yep, you got it.
Can I get some of the silver?
It should be some in here. Did I miss? Did I miss?
Oh, it's there? Okay.
Yeah, there's just one chunk. Glasses should be fine. No, that's tape from the rack. You're fine.
We put this in this, and then weigh this, and subtract that.
What is that?
This.
Yes, then you're correct.
All of it?
Yes.
I don't want to die.
No, you're not going to die. Just don't lick it. There you go. You can give me the small test tube back. When you're done with your small test tubes, you can give those back to me, and I'll take care of them for you. Your small ones, thank you. Thank you, thank you, thank you. When you're done with your tiny little test tubes, I'll take those back. Thank you, thank you, thank you, thank you, thank you. Okay. When you're done with your tiny test tubes, I'll take them back. They just dump the stuff out. There you go. Nice. Yes, you need another weight beaker.
It's the same size?
Yeah, they're no, 2 partners. Yep, you're each doing it. Partners. It'll help us in case there's like it gives us double the data to work with, in case one of them is not going right. But yeah, they're different amounts. It's just sticky from the tape. They're both good. They're both really good. Do you know glass weighs?
Yeah.
Okay, then dump that in there where you're wet.
So is this how we?
Uh-huh.
How much?
Yeah, pretty much.
I
Yeah.
got I went shopping and I got you this.
Oh, thank you, thank you. Thank you. Yep, that's it. That's just me. Make sure you put a little hook on the top so it hangs in there. Okay. Yep. Add some water to it and then just stir it till it dissolves. You got it. Okay, we have about 10 minutes left in class, a little bit under, so just kind of keep an eye on that. You need your 2 masses, and then you need to make your solution. Did you figure out what your masses are? Yeah, perfect. And you can even straighten this out a little bit so it straighten this part out so it hangs down fairly low in the test tube. Just pull it straight down. You don't even need that big a handle. Just do a tiny little handle. Look how much I've got. Just a tiny bit. Glass stirring rod in the box, in the tub, in the bottom. There's a glass stirring rod in the bottom. There we go.
And it has to be distilled water due to it not being conductive.
It's not the conductive. It's that there's chemicals in here that we don't want to be a part of our reaction.
45 to 50 milliliters. What grade?
Yeah, so just basically you'll see the 40 line that's on there somewhere in that range. Yep. Don't touch the nozzle to the solution. Fill the beaker, 40 to 50. So somewhere in, 40 to 50. There you go. That's kind of what you're trying to do. And then just put a little hook up on the top.
Does it have to be like turned like that?
It's nicer if it is. It gives a little bit more space.
Okay.
Yeah. Yep. Okay, so for your wire, this is kind of where you're trying to go.
Okay.
Like that. Did you use the distilled water or did you use tap water?
This.
That's good. Okay. All right. Okay. Okay.
They're getting 28 for that, and we were getting for
What-
when we weighed that.
So you should have between about 1 and 1.5 grams of silver nitrate.
Why is it coming out to 28? But that's right for us.
So
That's about
is that the mass with the glass and
Yeah.
the stuff in there? Yeah. So
And that's
2.39 minus 1 is like 1.39. Yeah.
okay. So yours is doing something funny.
What was the weight of your beaker?
It was like,
It was definitely not 0.17, not the beaker.
I know. Not like the beaker. I don't know. I like weighed the beaker like 3 different times and it all came out like.
Okay.
Can we pour this in?
I was like 26.
So pull this down longer so it's all the way down to the bottom because there isn't that much in here. So make that just long and tall. Do you have your small test tube? You don't. Let's do this. Okay, so we're going to do it this way. So hold on. Wait. Make sure that's a 0. See, it's not zeroed as part of your issue.
Before I did look at
Okay.
I like zeroed it out.
Okay, so it is right now 49.53. Right? It's okay. No, it's fine.
We can pour this. We can pour this.
I would. Okay, ready? So 49.53. There you go. And there's your new one. All right. Okay, so that just had water in it. Yeah, you can actually see the reaction starting. Did you remember to brush your copper?
No.
Just be a little bit on the side. I'm doing it. So you should get between 1 and 1. Okay. All right. Fabulous. So dissolve it. I just wrapped it around. I wrapped it around a pencil. Hey, nice. All right. Did you brush it off with silver with the? Okay, about to go. Then you can combine them. Okay. So make sure that your wire's kind of down towards the bottom. Down. You're good. But just make sure it's down towards the bottom. Yep, you're fine. Little hook at the top. Yeah, just so you don't lose it. Yep, that's fine. And then when you're ready, combine them together. Yep. When you're ready, combine them together. Don't forget, did you wipe off the copper wire with the steel wool? Okay. All right. We're at about 4 minutes remaining here. So we need to kind of get that going. There you go. Yeah. No, you guys are doing one. You're doing one.
Oh my gosh, that Max makes your eyes pop. I was gonna tell you.
Oh wait. So do I wash
This
this?
is sweet.
Or like what do I do with
Yep. Wash that in the sink. Yep. Nice.
Yeah, I did about 45. This one's ours, this one's theirs.
Yep. Okay.
Focus. This beats on your focus.
So you can just put that, just leave it on your center table right there. Any of your other materials, kind of wipe them off, put them back in your tub. Okay. Grab a paper towel, then wipe it up. All right, so you're gonna put your test tubes in the rack. Make sure you know which one is yours, which one's your partner's. Make a note, of some sort. Any of your other used materials, I'll take the small ones back, but anything else, let's rinse that out, clean up your materials, glass stirring rod, all that stuff. You can put it back in that tub. It's just water. At this point, it's just water. With what? You rinse this out in the sink. You just wash them in the sink and then put them back in the tub. Wash them in the sink, put them back in the tub. All right. We are done for today.
There we go. I am a professional cleaner. Can I just get those faster or do you need this?